Hello students, have you ever picked up a magnifying glass and noticed how the size of an object seems to change depending on how close or far you hold it? Sometimes the image looks much larger, sometimes smaller, and sometimes even upside down. Isn't that fascinating? Well, this magical trick is not magic at all, it's pure physics. It happens because lenses bend light in specific ways. Today, we are going to explore the lens formula, a powerful tool that helps us predict exactly where and how an image will form when light passes through a lens. Think of it as a mathematical rulebook that connects three important distances: the object distance denoted as u, the image distance denoted as v, and the focal length of the lens denoted as f. The formula goes like this: 1 divided by v minus 1 divided by u equals 1 divided by f. In other words, 1 by v minus 1 by u equals 1 by f. Here, v is the distance of the image from the lens, u is the distance of the object from the lens, and f is the focal length of the lens. So, every time you use a magnifying glass, a camera, or even your spectacles, this simple but elegant formula is secretly at work, helping to form clear images. By the end of this lesson, you'll not only understand the formula but also be able to use it to solve real-world problems, from predicting the size of an image in a microscope to understanding how projectors work. Alright students, now that we've introduced the lens formula, let's dive into how it is actually derived. Don't worry, this is not just about equations, it's about seeing how geometry and ray optics come together to explain something we observe every day. We begin with the idea that the principal axis of the lens acts as a reference line, or simply the x-axis. Think of it as the highway along which all distances are measured. Here's the important sign convention: distances measured to the right of the optical center O are considered positive, while those to the left are taken as negative. This keeps everything consistent and prevents confusion when we do calculations. Now, the derivation itself. We start by tracing two rays from the top of the object. The first ray passes parallel to the principal axis and then refracts through the focus. The second ray passes through the optical center of the lens without deviation. These two rays meet at a point on the other side of the lens, and that point gives us the image position. As you can see in the diagram, that's exactly where the object is brought into sharp focus. Using geometry of similar triangles, we arrive at a relationship between three distances: the object distance u, the image distance v, and the focal length f. Step by step, the derivation leads us to the famous lens formula, which is expressed as 1 divided by f equals 1 divided by v minus 1 divided by u. Where f is the focal length of the lens, v is the image distance, and u is the object distance. This formula is not just theoretical, it is practical. It tells us precisely how a lens forms an image, whether it's your camera lens focusing on a subject or a projector casting a sharp picture on the screen. Every time a clear image forms, this simple yet powerful equation is quietly working in the background. Now students, before we jump into applying the lens formula, we need to settle something very important: the sign convention. You see, without a proper set of rules, solving lens problems would be as confusing as trying to drive in a city where every street has no traffic signals. Chaos everywhere. That's why physicists agreed on a standard system of signs to keep our calculations neat and logical. Here's how it works. The object distance u is taken as negative when the object is placed on the left side of the lens. That's the usual case for real objects, like a candle in front of a convex lens. The image distance v is positive if the image forms on the right-hand side of the lens, meaning it's a real image. But if the image forms on the left, like in the case of a virtual image, then v is taken as negative. And what about the focal length f? Well, that depends on the type of lens. For convex lenses, which converge light rays, the focal length is positive. For concave lenses, which diverge rays, the focal length is negative. This little sign change makes all the difference when you're solving numerical problems. As you can see in the diagram, the object is on the left and the lens is forming two different possibilities, one real image on the right and one virtual image on the left. The sign convention helps us distinguish between these cases with absolute clarity. So, the next time you work with the lens formula, 1 divided by f equals 1 divided by v minus 1 divided by u, remember that every plus or minus sign tells you a story about where the image is and what kind of lens you're using. Without this rulebook, our formula wouldn't make sense at all. Alright students, let's put the lens formula into action with a real example. Imagine we place an object 15 cm in front of a convex lens whose focal length is 10 cm. The big question is, where will the image form? Step 1 is recalling the lens formula, 1 divided by f equals 1 divided by v minus 1 divided by u. Now step 2, let's substitute the values. Here, the focal length f is plus 10 cm because it's a convex lens, and the object distance u is negative 15 cm since the object is placed to the left of the lens. So the equation becomes 1 by 10 equals 1 by v minus open bracket 1 by negative 15 close bracket. Step 3 is simplifying. 1 by v equals 1 by 10 plus 1 by 15. If we take the LCM, that becomes 3 by 30 plus 2 by 30, which equals 5 by 30. So, 1 by v equals 5 over 30. Step 4, take the reciprocal. v equals 30 over 5, which simplifies to 6 centimeters. So step 5, the image forms at 6 centimeters on the right-hand side of the lens. And because it comes out on the opposite side from the object, we know it's a real image. As you can see in the diagram, the rays meet on the right, showing us exactly where the image appears. This simple calculation proves just how powerful the lens formula is. It allows us to predict image position precisely, whether it's in a microscope, a projector, or even the lens inside your eye. Now students, let's see how the lens formula works for a concave lens. Imagine placing an object 30 centimeters away from a concave lens with a focal length of 20 centimeters. Where will the image be formed? Let's carefully work this out together. Step 1. Recall the lens formula, 1 divided by f equals 1 divided by v minus 1 divided by u. Step 2. Apply the sign convention. Since it's a concave lens, the focal length is negative 20 centimeters. The object is on the left side, so the object distance u is negative 30 centimeters. Substituting these into the formula, we get 1 by negative 20 equals 1 by v minus open bracket 1 by negative 30 close bracket. Step 3. Simplify. 1 by v equals 1 by negative 20 plus 1 by 30. Taking the LCM, that becomes negative 3 by 60 plus 2 by 60, which equals negative 1 by 60. So, 1 by v equals negative 1 by 60. Step 4. Take the reciprocal. That means v equals negative 60 centimeters. Finally, step 5. What does this negative sign tell us? It tells us that the image is on the same side as the object, at 60 centimeters from the lens. And because it forms on the same side, it is not a real image, it's a virtual image. As you can see in the diagram, the rays appear to diverge, but if extended backward, they meet at a point on the left-hand side. This is why concave lenses always give us virtual, erect, and diminished images. That's exactly why they are used in things like peepholes indoors, so you can see a wide area in a smaller image. Alright students, let's quickly bring everything together. The lens formula, 1 divided by f equals 1 divided by v minus 1 divided by u, is our key tool to calculate the image position for any lens. No matter the situation, this formula keeps us anchored. For convex lenses, the focal length is positive. And depending on where the object is placed, these lenses can form real images, like those in cameras and projectors, or virtual images, like in magnifying glasses. On the other hand, for concave lenses, the focal length is always negative. And these lenses always give us virtual, upright, and diminished images, which is why they're used in devices like door peepholes. So to sum up, with just one simple formula and a clear set of sign conventions, we can predict how lenses bend light and form images in almost every optical device around us. From spectacles to microscopes, from cameras to telescopes, this principle is at work everywhere. I hope this journey through the lens formula has made you realize that physics is not just about equations, it's about understanding how light shapes the way we see the world. In our next session, we'll explore yet another fascinating concept of optics. Until then, keep observing, keep questioning, and keep seeing the magic of physics in everyday life.